In this video, we're going to introduce the idea of an optimization problem. So first thing I want to do is actually define what it means to optimize something. A situation is optimal if it is as good as it can possibly be. So to optimize something is to make as good as possible. Now, this part is a little bit subjective. How do we define personally what is something that is good? An example I like to talk about is my commute on a daily basis. My commute to campus on a daily basis used to consist of a drive from Royal Oak to Clinton Township. Now, on my way from home to work, there are a lot of different ways that I could define how to make that trip as good as possible. I don't know about all of you, but I tend to get very angry at people who don't use their turn signals on the road, so I try to avoid them at all costs. So let's talk about ways that I could optimize my commute in. Now, from a mathematical perspective, to optimize something generally is to make something as big as possible or to make something as small as possible. So, for example, I could minimize the distance traveled. Or I could minimize the amount of time spent on the road. I could minimize the amount of gas that I use. Now, let's be honest with ourselves. Here's what I would probably do if you know me at all. Maximize the number of Pokestops that I can hit on my way in. I'm not saying that I would ever drive and play Pokemon Go at the same time, but what I am saying is that when I'm turning from 14 Mile onto Main Street in Royal Oak, as long as I hit that light red, there are 3 Pokestops that I can hit right there, and then like 3 more and a gym that I can hit at the Blair Memorial Library just north of there. I'm just saying that that is one possible way that we could define how to make something as good as possible. Now, from a mathematical perspective, when we are optimizing something, we are going to be generally either minimizing or maximizing. Minimize or maximize. Now, that right there lets us know sort of the context of what we've been doing. We've been graphing functions and then trying to find local maxima and local minima, and the way that we do so is by finding critical points, points where the slope of a tangent line is either undefined or where it's equal to 0. So I realize this is a bit of a stretch in this section, but a lot of what we're going to be doing is setting up a function and then taking a derivative and setting it equal to 0 and solving for our variable. You know, like we did in section 4.1, 4.2, 4.3, 4.5, and now 4.7. You know what? This doesn't seem all that crazy anymore. Now, one big thing that is going to change, and I realize that this 2-word phrase just strikes fear into a lot of hearts, but it means that we're going to be dealing with word problems. Now, big thing regarding word problems is to identify what kind of problem we're dealing with. This is actually going to take us all the way back to the exercise that we did on the first day of class this semester. On the first day of the semester, I gave you all a get to know you exercise, and I asked you to tell me about the blankest thing that has ever happened to you. You could tell me about the best, or the worst, or the coolest, or the funnest, or the scariest. Essentially, what I was asking you to do was optimize your own life and give it to me in the form of a story. So anything that ends with an S, I realize I'm not an English teacher, but I did learn some things. I know how to English real good, real goodly. Anything that ends with est is referred to as a superlative. A superlative is referring to essentially the optimal form of something. If something is good, it can also be the best. Best would be the superlative of good. If something can be short, it can also be a shortest. That would be the superlative form of short. If something can be long, it can be a longest, which again, superlative form. So let's develop a little strategy for how we are going to approach these kinds of problems. So the strategy will be as follows. Step 0 is going to be to identify that the problem happens to be an optimization problem. And the way that we're going to do so is look for keywords like minimize or maximize, or one of those superlatives that I mentioned just a moment ago. As soon as you see a word problem that involves one of those words, chances are pretty good you are dealing with an optimization problem. Once you identify it as an optimization problem, we are going to define some variables. So to define variables is to pose the question, what quantity am I optimizing? That is referred to as the objective variable, because finding the value of that is now our objective. In addition to what quantity are you optimizing, you can pose the question, what other quantities are mentioned in the problem? What other quantities are mentioned in the problem? Chances are pretty good you are going to want to get the objective variable in terms of these other variables, in terms of quantities that are mentioned in the problem. After we do this, we are going to look for relations involving these variables. Define relations among the variables. For example, if I were trying to find the largest possible area of a rectangle, chances are pretty good I would need variables for the length of that rectangle and the width of that rectangle. So define any relations among the variables. Then perform substitutions if necessary. Perform substitutions to get the objective variable in terms of only one variable. As you progress through your calculus courses, there will be a technique in multivariable calculus where you are able to keep an objective variable in terms of however many variables you want. For now, though, since we only have access to one variable, we want to make sure that the objective variable is in terms of only one variable, probably a variable like time or x or something along those lines. Next up, determine if the variable that I mentioned, determine if the independent variable has a domain associated with it. If it has a domain, then that means that there are endpoints for the particular interval that we're working with. In the event that there is a domain associated with it, you will need to test those endpoints to see if the endpoints could be a maximum or minimum as well. Now, if it does have a domain, or even if it doesn't, you are going to determine all critical points. For the objective variable. Determine all critical points for the objective variable. Once you have done this, chances are pretty good you are going to have several different values of the objective variable. If you're trying to maximize it, go with the largest value you see. If you're trying to minimize it, go with the smallest value that you see. And finally, interpret your results. This will usually involve a statement of, in order to, excuse me, for example, maximize the area of the rectangle, you need to set the length equal to this and the width equal to this. So next up, we'll do some examples.